Hello students, I am Tulika Banerjee. Today I bring you the next learning episode in BSc Forensic Science on an important unit of the paper titled Fingerprints, that is Chemical Method for Detection of Latent Fingerprints, Part 3rd, Amino Acid Specific Reagents. In this lecture, you will be studying about the importance and significance of amino acids as it is an important constituent of sweat residue. In addition to it, you will be studying the number of reagents that fix amino acid constituents of sweat to develop latent fingerprints. You will also know about some of the products formed by the interaction of developing reagents with amino acids. At last, we will wind up this module or this lecture by knowing the number of amino acid specific reagents that are used for detecting latent fingerprints in actual casework investigations. And we will focus on DFO, that is 1,8-diazofluorane 9-one, by studying its methodology, procedure adopted for developing latent fingerprints by the DFO reagent and a comparison of DFO reagent with Nanhydrin reagent. Let us start our today's lecture with a brief look at what we will be learning regarding the modules today. First is amino acid specific reagent for detection of fingerprints, then we have amino acid reagents, then we have Nanhydrin analogues, then is DFO, and last is the conclusion. Dear student, let us start today's lecture with amino acid specific reagents for detection of fingerprints. Amino acids are an important constituent of fingertip sweat. When a finger touches a surface, these analogues are deposited thereon as sweat residue. This deposition, called latent fingerprint, contains several other chemicals such as chloride, phosphate, sodium, potassium and ions, as well as fatty acids, carbohydrates and vitamins. However, unlike other sweat constituents, amino acids neither interact with the cellulose component of paper, cardboard, wood and other porous surfaces, nor do they migrate within the substrate. As a result, the reagents that give colored derivatives on interaction with amino acids render visibility to both fresh and old fingerprints on a wide array of surfaces. It is therefore not surprising that amino acid specific reagents have been the state of art strategy for paper exhibits for the past many decades. The amino acid components of sweat may be tagged with a number of reagents. The first and for many years the only amino acid based reagent that was standardized was Nanhydrin. For this reason, it has been the most popular one. Over the years, many more amino acid specific reagents have been investigated for detecting latent fingerprints. We review this significance in this lecture. First is Nanhydrin. The Nanhydrin treatment is one of the premier techniques for development of the latent prints on porous surfaces such as paper. Nanhydrin, as shown on your screen, reacts with amino acid content of sweat, forming a purple colored complex called as Ruhmann's purple. Broadly, the procedure for developing latent finger marks involves spraying the Nanhydrin solution on the surface containing the impression from a distance of about 6 inches. After the solvent evaporates, the solution is sprayed again. The surface is then heated for a short time without allowing it to come into contact with the heat source. If quick development is not required, the item may be allowed to dry at room temperature. Better results are obtained by natural drying. A sample fingerprint developed by Nanhydrin method has been shown on your screen. However, the concentration of amino acids in sweat is quite low, as a result of which the developed prints do not show sharp contrast. To improve the clarity, prints are post-treated with salts of group 12 elements of the periodic table. This results in conversion of non-fluorescent Rohmann's purple into a photoluminescent complex. The color of Nanhydrin developed fingerprints changes from red to orange on post-treatment with zinc chloride or cadmium nitrate. Subsequent observation under an argon ion laser produces appreciable luminescence. The intensity of photoluminescence increases at low temperatures, that is around 77 Kelvin. Till the early 1980s, it was endeavored to improve the Nanhydrin method by altering the solvents, the composition, or by pre-treatment or post-treatment of developed prints. Later, a different approach was adopted. Several derivatives of Nanhydrin were synthesized and tried out for developing latent fingerprints. It was anticipated that the derivatives of Nanhydrin possessing the diketone function would react with amino acid content of the sweat in the same way as the Nanhydrin itself. With several Nanhydrin analogues, this expectation turned out to be true. The most promising Nanhydrin analogue is benzo-F-Nanhydrin. This reagent develops dark green colored fingerprints with excellent resolution. Improved sharpness was observed on treating benzo-F-Nanhydrin developed fingerprints with zinc chloride, followed by examination under an argon laser. However, still better results were obtained with the frequency doubled neodymium yttrium aluminum garnet, that is ND-YAG laser. The emission wavelength of the latter device, that is around 532 nanometers, closely matched with the absorption band of the benzo-F-Nanhydrin amino acid zinc chloride complex. An isomer of benzo-F-Nanhydrin, that is benzo-E-Nanhydrin, gives good quality pink colored prints. Another Nanhydrin derivative which develops latent fingerprints with appreciable degree of sensitivity is 5-methoxy-Nanhydrin. On paper, this reagent produces fingerprints as efficiently as Nanhydrin. Yet, fluorescence after zinc chloride treatment is considerably stronger than with Nanhydrin, particularly when examination is carried out by a copper vapor laser. 5-methoxy-Nanhydrin has also proved useful for developing fingerprints on counterfeit currency. Benzo-F-Nanhydrin and 5-methoxy-Nanhydrin offers operational advantages over Nanhydrin. Prints developed with either of these reagents showed stronger room temperature luminescence after zinc or cadmium treatment in comparison with similar prints developed with Nanhydrin. These were also effective for lifting fingerprints on cardboard where background luminescence precluded the successful enhancements of Nanhydrin developed prints. Then we have 5-methoxy-Nanhydrin. Another Nanhydrin derivative which develops latent fingerprints with appreciable degree of sensitivity is 5-methoxy-Nanhydrin. Then we have fluorescamine. Fluorescamine, the structure shown on your screen, is a spiro compound that is not fluorescent itself, but reacts with amino acids to form highly fluorescent products. Hence, it has been used as a reagent for the detection of amino acids and peptides. It is also a fingerprint development reagent. A solution of 20 milligrams fluorescamine and 0.5 ml of triethylamine in 100 ml of acetone of according to pH 9 to 11 is sprayed on the surfaces containing the finger mark. The surface is dried and observed under an argon laser. sharp and clear fingerprints can be rendered visible. Next is tooth-aldehyde. Tooth-aldehyde reagent, the structure of which is shown on your screen, is used as a very sensitive fluorescent reagent for assaying amines or sulfhydryl in solution, notably contained in proteins, peptides and amino acids. As a result, it also reacts with amino acid and protein components of sweat residue to reveal latent fingerprints. On examination under an ultraviolet lamp or an argon laser, the developed prints are enhanced due to fluorescence. Two solutions are required when tooth-aldehyde is to be used as a fingerprint reagent. Solution A is prepared by dissolving 2.5 grams of boric acid in 95 ml of distilled water. The pH of the solution is adjusted at 10.6 with 6 molar potassium hydroxide. To the solution, 0.3 ml of 30% detergent and 0.2 ml of 2-mercaptoethanol is added. Solution B is prepared by dissolving 200 milligrams of tooth-aldehyde in 2 ml methanol. Solution B is mixed with solution A. The mixture is then sprayed on the exhibit. On drying, the surface is examined either under an ultraviolet lamp or under an argon laser, whereupon fingerprints are rendered visible. The next reagent is dansyl chloride. Dansyl chloride, the structure of which is depicted on your screen, reacts with primary or secondary amines, amino acids and proteins to produce stable blue or blue-green fluorescent sulfonamide adducts. It is widely used to determine protein sequencing and for amino acid analysis. It may also be used to label hydroxyl and carboxylic acid functional groups. In forensic applications, it is a fingerprint reagent. For detecting latent fingerprints, the composition is prepared by dissolving 10 milligrams of dansyl chloride in 20 ml of acetone. The solution is diluted by adding 80 ml of freon. The test solution is sprayed onto the surface and allowed to dry. Clear fingerprints can be observed upon ultraviolet illumination. The next reagent we have over here is 4-dimethyl aminocinnamaldehyde. The structure of 4-dimethyl aminocinnamaldehyde is shown on your screen. The test solution is prepared by dissolving a mixture of 4-dimethyl aminocinnamaldehyde, that is around 0.014 molar, and sulfuric acid, that is around 0.05 molar, in ethanol taken in 350 ml. The solution is further diluted by adding ether taken around 650 ml. The mixture is sprayed on the article, and on drying, the fingerprints may be observed under ultraviolet or laser light. The background coloration, if any, may be reduced by keeping the developed prints in the dark for a few days. The reagent is, however, not good at developing old prints. 4-dimethyl aminocinnamaldehyde may also be used as a fumigant for visualizing fingerprints on a wide range of surfaces. The next reagent that we have over here is 4-chloro-7-nitrobenzo-2-oxa-1,3-diazole. The 4-chloro-7-nitrobenzo-2-oxa-1,3-diazole's structure has been shown on your screen and is used for fluorogenic detection of latent fingerprints on multicolored paper. About 0.1 grams of 4-chloro-7-nitrobenzo-2-oxa-1,3-diazole is dissolved in a mixture of 10 ml acetone and 90 ml fluoresceol. Colored paper is dipped in the solution for a few seconds, air dried and heated for 2 minutes. The developed prints are examined with blue light, that is under 440 nanometers filter, and observed through a 580 nanometers orange filter in a dark room. Then we have 8-anilino-naphthalene 1-sulfonate. 8-anilino-naphthalene 1-sulfonate structure has been depicted on your screen and has proved to be a valuable and sensitive reagent for detection of fingerprints on greasy and porous surfaces. The developed fingerprints, when impinged with long wavelength ultraviolet light, show bright yellow fluorescence against dark background. Rapid development, no heat requirement, and simplicity are some of the other advantages of this technique. About 1 gram of 8-anilino-naphthalene 1-sulfonate is dissolved in 5 ml of methanol, and the resulting solution is mixed with 200 milliliters of freon. After the two layers separate out, molecular sieves are added to remove the methanol, as it causes running of ink on scripted documents. After spraying the test solution on sample fingerprints, the surface is allowed to dry for about 1 minute. It is then examined under long wavelength ultraviolet light, whereupon fingerprints are rendered visible. The next reagent over here is 7-nitro-4-benzofuranzyl ether. 7-nitro-4-benzofuranzyl ethers are fluorogenic reagents that can develop latent fingerprints on paper with a high degree of sensitivity. These may be used both in solution form as well as in vapor phase. Although the development is faster when a solution of the reagent is used in vapor phase detection, there is a smaller background fluorescence and discoloration. The most important compound of this classification, which is mostly used for latent fingerprint detection, is 4-methoxy-7-nitrobenzofuran. Its structure has been shown here. The spray solution is prepared by dissolving 100 milligrams of 4-methoxy-7-nitrobenzofuran in 1 ml acetonitrile and diluted with 100 milliliters of fluoresol. Samples bearing latent fingerprints are dipped into the test solution for 15 seconds and then air dried. These are then heated in an oven to 110 to 120 degrees centigrade for 10 to 15 minutes. Clear and sharp fingerprints develop. For vapor phase application, about 20 milligram of crystal of the compound are placed in a glass beaker and fingerprint samples are suspended about 15 centimeters from the base of the container. The beaker is covered with a thin aluminum foil and heated in an oven to 60 to 95 degrees centigrade for a period of about 1 to 7.5 hours, whereupon the fingerprints are visualized. The next reagent is 1,2-indendione. The reagent 1,2-indendione develops excellent quality fingerprints on porous items by reacting with amino acid content of sweat residue. It is specifically useful for detecting prints on bank checks and thermal paper. Its structure has been depicted over here. The test solution of the reagent is prepared by dissolving 2 grams of 1,2-indendione in 70 milliliters of ethyl acetate. The contents are diluted to 1 liter by adding 930 ml of petroleum ether. The solution is sprayed over the article bearing latent fingerprints and then heated in an oven for 20 minutes at 100 degrees centigrade. The fingerprints so developed are illuminated with light of 515 nanometer wavelength and observed through orange goggles. Finally, these are photographed. Next, we have amino acid specific reagent and a Nanhydrin analog, that is DFO, or better known as 1,8-diazofluorane 9-one. DFO is an amino acid sensitive reagent which develops latent fingerprints on porous surfaces like paper and wood. On reacting with the fingerprint residue, it gives a pale pinkish purple product. The reaction proceeds through the formation of intermediate yields and is similar to that between Nanhydrin and the amino acid content of sweat deposition. However, while the reaction of amino acids with Nanhydrin yields a non-fluorescent product, the corresponding reaction with DFO gives a luminescent derivative. The fluorescent nature of the amino acid DFO reaction product helps in developing weak chance prints that are often encountered at crime scenes. It also assists in detecting fingerprints on multicolored and glossy papers. Figure here shows one half of a representative sample fingerprint developed on paper with the aid of DFO reagent. The spectral characteristics of the fluorescence produced by DFO developed fingerprints have been investigated. It has been inferred that the fluorescent excitation wavelength occurred at about 470 nanometers, while the corresponding emission wavelength was centered at about 570 nanometers. When illuminated with green light, the developed fingerprints show strong fluorescence, which is viewed or photographed through an orange or red filter. The enhancement afforded due to fluorescence is shown on your screen. Some printing inks fluoresce under these conditions and therefore interfered with fingerprint detection. However, the optical brighteners present in paper do not hinder the visualization of prints. Fluorescent fingerprints visualized by DFO method normally reveal more details and clarity than those shown by the Nanhydrin developed imprints. Next is regarding the methodology. The exhibit on which latent fingerprints needs to be developed is dipped in the DFO solution. The solvent of choice for preparing the reagent is 1,1,2-trichlorotrifluoroethane, abbreviated as CFC-113, but generally known by its common name Fluoresce. Lately, however, this compound has been banned due to its role in depletion of stratospheric ozone. Methanol, acetic acid or petroleum ether serves as alternatives. A mixture of hydrofluoroether and trans 1,2-dichloroethene is almost as effective than CFC-113. The following procedure, subjected to minor variations, is normally adopted for developing latent fingerprints by the DFO reagent. The test solution is prepared by dissolving 0.5 grams of DFO in 1 liter of the solvent in a reagent bottle. The surface bearing the latent fingerprint impression is immersed in the reagent for 5 seconds, dried, re-immersed for 5 seconds and heated at 110 degrees centigrade for 10 minutes. Under white light, pink-purple ridges are rendered visible. The surface is illuminated with a radiation of 470 nanometers wavelength and fluorescence is observed through a 570 to 600 nanometers filter. The luminescence is at its maximum immediately after the heat treatment and then decreases slightly with time due to the absorption of ambient humidity. The luminescence may be restored to its original intensity by reheating the prints. A comparison of DFO reagent with Nanhydrin reagent. Both the DFO and Nanhydrin reagents are meant to detect latent fingerprints impinged on porous items like paper and cardboard and unpolished wood. It is therefore pertinent to outweigh the utility of one reagent with respect to the other. The DFO technique offers the following advantages over the Nanhydrin methodology. First, with DFO, a strong room temperature luminescence of developed prints is observed without any secondary treatment. Against this, the Nanhydrin developed prints have to be post-treated with a suitable metal salt to produce luminescence. Good results are obtained if the exhibit is cooled to 200 degrees centigrade during the fluorescence examination. With DFO reagent, results are obtained in a relatively short time of 30 minutes. Nanhydrin, on the other hand, develops fingerprints at room temperature in about 2 hours. For faster development, the surface in question has to be heated to about 80 degrees centigrade. For improved results, heating should be carried out in a humid atmosphere. On an average, DFO reagent develops 3 times more fingerprints than Nanhydrin. If DFO reagent fails to detect a latent impression, Nanhydrin method can still be tried out on the same surface. However, if Nanhydrin reagent does not develop a particular imprint, DFO method cannot be extended for its detection. The DFO method has the following demerits as compared to the Nanhydrin technique. A high-powered light source with appropriate filter must be available for observing luminescence of DFO developed fingerprints. Otherwise, weak impressions will not be detected. If the surface on which latent fingerprints are to be developed shows background fluorescence, the utility of the DFO method is curtailed. DFO reagent does not give satisfactory results on heat-sensitive items like thermal paper, window envelopes and labels on polyethylene articles. DFO reagent is costlier than Nanhydrin. The working solution of DFO reagent is not very stable and tends to become cloudy. Dear students, let us now conclude this lecture. Latent fingerprints may be visualized by a legend of amino acid specific reagents. Over the years, Nanhydrin has been branded as the most efficient amino acids tagging compound as far as detection of latent fingerprints is concerned. However, the reaction product of Nanhydrin and amino acids is non-fluorescent and only after post-treatment yields luminescent product. The other amino acid specific reagents are advantageous in that these produce fluorescent derivatives on reacting with amino acid content of sweat residue in one step. 2 of these reagents, that is 1,2-indiene and 1,8-diazofluorane-9-one, have been validated for detecting latent fingerprints on porous surfaces. The detection methodologies have been standardized and these procedures are being used in casework investigations. With all these information, here we come to the end of today's lecture. Do keep in mind what we have discussed today. I'll be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQs, quizzes, LORs, etc. Thank you for your time today. I'll see you in the next lecture. Have a great day.